Something is wrong with the most important spacecraft NASA has built in 50 years, and the people who know exactly what it is are not talking loudly about it. They are talking quietly, in technical briefings, in engineering review meetings, in the careful language of people who understand that what they found during testing does not have a clean, comfortable answer yet. And what makes this deeply unsettling is not that NASA discovered a problem, because problems are expected in aerospace. Engineering, they are part of the process, they are why testing exists. What makes this unsettling is the specific nature of what they found, where they found it, and the fact that the Artemis II crew is scheduled to sit on top of the system and travel farther from Earth than any human being has traveled in over half a century. During the uncrewed Artemis I mission in November and December of 2022, NASA sent the Orion capsule on a 25-day journey around the Moon and back, the longest deep space mission ever flown by a crew-rated spacecraft, designed specifically to test every system before human lives were placed inside it. And when Orion came home and the recovery teams pulled it from the Pacific Ocean and engineers began the meticulous process of inspecting every surface, every component, every tile and seal and sensor, they found something on the heat shield that nobody had predicted, nobody had modeled, and nobody had a fully satisfying explanation for, and that discovery has been sitting at the center of NASA's most serious engineering concern ever since. The heat shield is not a minor component, it is the single most critical piece of survival hardware on the entire spacecraft, the only barrier between the crew and temperatures exceeding 5,000 degrees Fahrenheit during re-entry, a charring ablative material called avcoat that is designed to burn away in a controlled and predictable pattern, absorbing heat and protecting the capsule behind it. And what engineers found when they examined the Artemis I heat shield was that the charring was not controlled and it was not predictable. Large chunks of the ablative material had broken away during re-entry in a pattern that was completely inconsistent with what the computer models had simulated, leaving behind unexpected voids and uneven burn patterns across the shield surface. And while the spacecraft survived because the overall thermal protection system performed within acceptable limits, the margins were tighter than anyone had designed for, and tighter margins in aerospace. Engineering are not a minor footnote, they are the difference between a successful mission and a catastrophic one. NASA spent the better part of 2 years investigating this anomaly, running thermal models, analyzing material samples, testing small-scale heat shield panels in arc jet facilities that simulate re-entry heating, and what they found deepened the concern rather than resolving it cleanly. The avcoat material was behaving differently under actual deep space re-entry conditions than it behaved in ground testing, specifically in the way the material responded to the combination of high heat, pressure, and the particular angle and velocity of a lunar return trajectory, which is significantly more demanding than a low Earth orbit re-entry, and the models that engineers had trusted for years were not capturing this behavior accurately because there was simply no real-world data to calibrate them against. Artemis I was the first spacecraft to return from lunar distance in over 50 years, and the environment it experienced during that re-entry was, in a very real sense, unmapped territory. Now here is where the story becomes more layered and more troubling, because the heat shield anomaly is not the only thing that came out of Artemis I testing that has engineers in a state of quiet concern. It is the most visible and most publicly discussed issue. But there are deeper systemic questions that the Artemis I data raised about how Orion performs in the actual deep space environment versus how it was designed to perform in simulation, and one of the most significant of these concerns involves the spacecraft's life support and environmental control systems, which during Artemis I showed unexpected thermal behavior in certain components due to the radiation and vacuum conditions of deep space, conditions that ground testing facilities can approximate but never perfectly replicate. And these thermal anomalies were not dangerous for an uncrewed vehicle but become meaningfully more complex when 4 human beings are inside generating body heat, consuming oxygen, producing carbon dioxide, and depending on those systems to maintain a precise balance of pressure, temperature, and breathable atmosphere for 10 days continuously. There is also the question of what Artemis I revealed about the Space Launch System itself, the rocket that will carry the crew, specifically in the performance of its core stage engines and the behavior of the liquid hydrogen and liquid oxygen propellant systems under the extreme stresses of actual launch, where vibration profiles, acoustic loads, and thermal gradients combine in ways that even the most sophisticated computational models cannot perfectly predict, and post-flight analysis of. The SLS engine data showed performance deviations from predicted values in several areas that engineers flagged for review, deviations that were within the vehicle's design margins but that nonetheless represented unknowns in the system's behavior that needed to be understood before a crew sat on top of it. And then there is the radiation data, which in some ways is the most quietly alarming finding of all. because Artemis 1 carried a suite of radiation measurement instruments including two mannequin torso phantoms named Helga and Zohar, one with a radiation vest and one without, and the data they returned from the lunar trajectory showed radiation dose rates in the deep space environment that, while not surprising to physicists who study space weather, provided the first real measured confirmation of just how aggressive the deep space radiation environment is for a human-sized target, with dose rates significantly higher than what astronauts experience on the International Space Station, and the data captured a period of moderate solar activity, not a major solar particle event, meaning that under more active solar conditions, which are more likely now given that we are near the peak of solar cycle 25, the doses measured could be substantially higher than what Helga and Zohar recorded, and the radiation vest worn by Zohar did provide measurable protection but not complete protection, with certain organs and tissues still receiving doses above the levels NASA considers acceptable under its long-term astronaut health guidelines. What makes all of this particularly interesting from a scientific standpoint is that it is revealing a gap that has existed in human spaceflight for 50 years, a gap in our actual empirical knowledge of how spacecraft systems, materials, and human bodies behave in the true deep space environment beyond Earth's magnetic field, a gap that existed because after Apollo 17 in 1972, no human being and no human-rated spacecraft went there again, and the models and simulations that engineers built in the decades that followed were extrapolations, sophisticated and carefully constructed extrapolations, but extrapolations nonetheless, and Artemis 1 is now showing us where those extrapolations were imperfect, which is both exactly what the mission was designed to do and simultaneously a reminder of how much remained unknown. NASA's official position is that the findings from Artemis 1 are being systematically addressed, that the heat shield anomaly is understood well enough to proceed with a crewed mission, that the life support anomalies have been analyzed and corrective measures have been implemented, and that the SLS propulsion data has been reviewed and cleared, and it is important to say clearly that NASA is not hiding a crisis. They are not proceeding recklessly, and the engineers and flight directors making these decisions are among the most rigorous and capable people in the world at assessing risk, but the scientific community watching from outside is asking a question that is harder to answer with confidence, which is whether the Artemis 1 data has been fully understood or whether it has been understood well enough to proceed. And those are meaningfully different things in a domain where the gap between well enough and fully can be measured in human lives. Several aerospace engineers and independent researchers who have reviewed the publicly available post-flight data have noted that the heat shield material loss patterns are still not fully explained by the corrective models NASA has developed, that there are scenarios within the known uncertainty bounds of the re-entry environment where the thermal protection margins for a crewed Artemis 2 mission could be tighter than what NASA's official analysis assumes, and while these voices are not saying the mission should not fly, they are saying the confidence level is lower than it should be for a human mission, and that is a statement worth sitting with. The broader implication of everything NASA found during Artemis testing is something that reaches well beyond this one mission. It is a revelation about the true cost of the 50-year gap in deep space human exploration, a gap that allowed institutional knowledge to fade, that meant the generation of engineers who actually flew Apollo had retired or passed away. That forced the current generation to rebuild deep space capability largely from computational models and archived data, and the lesson that Artemis 1 is teaching, quietly, in the language of anomalous heat shield erosion and unexpected radiation measurements, is that some knowledge cannot be fully recovered from models, it must be earned again from real flights, from real data, from real systems encountering the real environment, and that process of earning knowledge back is inherently a process of discovering what you did not know you did not know. For human beings are preparing to sit inside that Orion capsule in the coming months, trusting the heat shield, trusting the life support, trusting the radiation analysis, trusting that every anomaly found during Artemis 1 testing has been understood completely enough to keep them alive, and the scientists who are quietly concerned are not worried because they think NASA has been careless. They are worried because they understand better than anyone that the deep space environment is not a laboratory, it does not repeat its conditions on demand, it does not give second chances, and the questions that Artemis 1 raised have been answered with the best tools available, but the universe has a way of asking questions that the best tools available are not yet able to fully answer, and the most honest thing anyone can say about what NASA found during Artemis 2 testing is this: we know more than we did before, we are more prepared than we were, and there are still things out there in the dark between the Earth and the Moon that we do not yet fully understand. And perhaps that is exactly why we have to go.